Welcome to class, everyone. I am absolutely thrilled you're joining me for today's explainer, because we're essentially turning our time together into a virtual science lab. Okay, let's just dive right into this. Picture this. There's a young kid named Keshav, right? And on a recent vacation, he's out at night watching this incredible dance of hundreds of fireflies, just flashing their lights in this gorgeous natural performance. But later, he's riding this evening bus back to the city, staring out at the moonlit landscape, and his inner scientist just kicks into overdrive. He starts wondering, how exactly do fireflies glow? And for that matter, how does moonlight actually work? Well, today, we are going to explore the magic of light and answer those exact questions. So, here is our game plan for the lab today. 1. Luminous or not. 2. The straight path of light. 3. Testing materials with light. And 4. Changing direction with mirrors. All right, let's kick things off with Section 1, Luminous or Not, Discovering the Sources of Light. To start, we've got to tackle that central mystery of the night sky that Keshav was pondering on his bus ride. I'm throwing this question directly at you, my class of focused learners. Does the moon actually produce its own light? Think about it for a second. Picture that bright moonlight shining down on a dark road. Does that light actually originate from the moon itself?
Well, if you said no, you nailed it. The moon absolutely does not emit its own light. It's really just a giant reflector hanging up there in the sky. And this is actually a perfect way to look at how we categorize objects in science. On one hand, we have luminous objects. These are the rule makers that emit their own light. We're talking the sun, Keshav's fireflies, a trusty torch, or LED lamps. On the other hand, you have non-luminous objects. These guys do not emit light, they only reflect it. The moon, a random cardboard box, mirrors, they all fall into this bucket. The moon is literally just bouncing back the light emitted by the sun.
Moving right along to Section 2, the straight path of light. We're going to test exactly how light travels. Now that we know where light actually comes from, it's time for our first hands-on investigation to discover light's most stubborn rule. Imagine setting up this classic matchbox activity. First, you take 3 matchboxes and pierce a tiny hole right in the exact center of each one. Next, you line them up perfectly straight, ensuring all those holes are at the exact same height. Then you place a torch on one side and a little cardboard screen on the other. Turn the torch on, and sure enough, you get a bright spot on the screen. But here comes the twist. What if you take that middle matchbox and slide it just slightly out of alignment? Class, what's your prediction here? What's going to happen to that bright spot? If you guess that the light completely vanishes, you are 100% correct. The second those holes are out of line, boom, the light spot is gone. And this brings us to a massive scientific conclusion. Light travels in a straight line. It absolutely refuses to curve, bend, or swerve around that misaligned cardboard. It is strictly a straight path traveler. Which brings us to Section 3, Testing Materials with Light. Let's see what happens when objects get in that straight path. Let's enter the next phase of our lab. We're going to test what happens when different everyday items try to block light's path. And honestly, this is a fantastic little test. You can literally try at home tonight. Just go into a dark room, turn on a torch, and aim it at the wall. Then hold different test objects right in front of the beam and observe whether the spot of light still manages to hit the wall behind your object. Let's check out our lab results, because different materials react in wildly different ways. When we test something like glass, the observation is super clear. The light passes fully through to the wall. But throw some tracing paper in there and the light only passes partially. The spot on the wall gets super dim. And if you test cardboard, the light doesn't pass through at all. The wall just stays totally dark. So let's put some proper scientific names to these reactions, shall we? First up, we have transparent. Transparent materials allow light to march right on through almost completely. Because a window pane is transparent, those straight lines of light from our torch just sail right through it and hit the wall with full brightness. Next, we've got translucent. These are your fuzzy middle materials that only let light pass through partially. It's exactly why the torch beam looked so faint and diffuse when we threw the tracing paper in front of it. And finally, opaque. Opaque materials do not let any light pass through whatsoever. Cardboard is perfectly opaque. And here is the really cool part. Because opaque objects act like a brick wall for those straight light beams, they leave a dark, lightless patch right behind them. And you know what that is? That's a shadow. So the next time you're walking outside and see your shadow on the pavement, just remember, you are the opaque object standing right in the straight path of the sun. All right, our final stop is section 4, changing direction with mirrors. Time to try breaking that straight line rule. So I have a challenge for you. We just proved that light only travels straight and that opaque objects completely block it. But is there any possible way we can force light to change its direction? To figure that out, let's run a grand finale experiment using just a basic mirror and the sun. First, you'd find a shiny flat plain mirror, has to be perfectly flat, not curved, and take it outside. Then you let those bright, straight rays of sunlight hit the shiny surface. And finally, you just tilt the mirror to redirect or bounce that light right onto a wall that's sitting in the shade.
You can actually picture this perfectly in action, catching a straight beam of brilliant sunlight, and instead of the light passing through or getting blocked, that shiny surface just grabs the beam and perfectly redirects it. It creates a brand new, totally straight line shooting right into the dark.
Now, the official scientific vocabulary term for this light-bouncing magic, that's reflection. Reflection is simply the change in direction of light when it falls upon a shiny surface or a mirror. The light is still stubbornly traveling in straight lines, but the mirror is acting like a perfect bounce pad, sending it off on a brand new path. As we wrap up today's explainer, I want to leave you with one final, kind of mind-bending question. Since the moon, our mirror experiments, and basically everything on Earth relies on the sun as our primary luminous source, what would actually happen if the sun just suddenly stopped emitting light? Would everything around us just instantly plunge into pitch black? The answer is actually no. It takes about 8 minutes and 20 seconds for the sun's light to travel across space and reach Earth. So if the sun were to suddenly switch off right this second, we literally wouldn't even know it went dark for over 8 whole minutes. Light is incredibly fast, but it still has a physical journey to make. Thank you so much for joining me in the lab today. Keep an eye out for all the luminous and non-luminous objects around you, keep testing those shadows, and let me leave you with this. If it takes light over 8 minutes to reach us from our own sun, how long do you think it takes to reach us from those tiny little stars we see in the night sky? I'll let you chew on that, and I'll see you for our next science adventure.